Hello, everybody out there in YouTube land. Good times for all. There's actors and Bala here if you prefer. In today's video, we're going to be discussing and going over a video of a MIT physics professor, former MIT physics professor, I should say, Walter Lewin, and his lectures on his 802 physics course covering electricity and magnetism. This will be the fourth lecture in a series of many, 40 of them actually, 39. It's amazing what you can get for free here on the internet. A little background on Walter Lewin. He is an amazing teacher. He has taught me so much, and I've never even seen the man. Just from what I've learned, he's a great teacher. He has a great way of explaining things. And he explains to you that, like in the books, I'll play it for you, but what he says, I want you to hear it, is that he's not going to teach you what's in the book, but what he teaches you will go with what is in the book and vice versa. It will help you see beyond a bunch of equations and numbers and actually see the beauty of physics and understanding how electricity and magnetism work. He's a very passionate person when he speaks about these topics. And yeah, he was a very good teacher, a great teacher, still is. He does lessons here on YouTube for free. So yeah, go check him out. Just lectures by Walter Lewin. They will make you love physics. Amazing teacher. This is from his first lecture. I play this before. I'm going to play it before everyone because he kind of explains what's going to be happening throughout the course and what he's hoping to teach these students. So let's turn this on. Like so.
Will in general not be a repeat of your book, but they will be complementary to the book. Book will support my lectures, and my lectures will support the book. You will not see any tedious derivations in my lectures. For that we have the book. But I will stress the concepts, and I will make you see beyond the equations, beyond the concepts. I will show you, whether you like it or not, that physics is beautiful. And you may even start to like it. I suggest you do not slip up, not even one day. 802 is not easy. We have new concepts every week, and before you know, you may be too far behind. Electricity and magnetism is all around us. We have electric lights, electric clocks, we have microphones, calculators, television, VCRs, radio, computers. Light itself is an electromagnetic phenomenon, as radio waves are. The colors of the rainbow in the blue sky are there because of electricity, and I will teach you about that in this course. Cars, planes, trains can only run because of electricity. Horses need electricity because muscle contractions require electricity. Your nerve system is driven by electricity. Atoms, molecules, all chemical reactions exist because of electricity. You could not see without electricity. Your heart would not beat without electricity. And you could not even think without electricity, though I realize that even with electricity, some of you may have a problem with that. The modern picture.
Okay. So that's all of that one I really wanted to share with you. It was just him explaining how electricity controls everything that at least we can really sense. Every chemical reaction, every muscle contraction, every light source that you see, every sound that you hear. You know, pretty much just about every sense you can think, your nervous system, everything about us is electric. It's all electricity. Now, some of it, I believe, is somewhat of an assumption almost, because they do not understand the subatomic. Um, they don't know what's causing, the strong nuclear force and the weak nuclear force. He admits this in lecture 1. They don't know what's going on. And for thousands of kilometers, electricity holds the earth together. And gravity only comes into effect when you're dealing with the moon, planets, the stars, the solar systems. He says all of this in lecture 1. In lecture 2, he introduces electric fields and how they act, how they are formed, and how they get their shape. In lecture 3, he explains a lot of neat things. I'm thinking about doing 5 of them and then doing an overview and pulling out the real juicy parts, because a lot of it is a lot of mathematical equations and how to it's googly-garb to me. That's not the stuff I really want to understand. I want to understand the actual physical forces behind what's going on and how you can, test them yourself. So, without any further ado, we're going to go down here to lecture number 4. Electrostatic potential, electric energy, and equipotential surfaces. I watched this one earlier. This one, it really blew my mind.
We're going to talk about, again, some new concepts. And that's the concept of electrostatic potential, electrostatic potential energy, for which we will use the symbol U, and independently, electric potential, which is very different, for which we will use the symbol V. Imagine that I have a charge Q1 here, and that's plus charge. And here I have a charge plus Q2, and they have their distance R apart, and that is point P. It's very clear that in order to bring these charges at this distance from each other, I had to do work to bring them there, because they repel each other. It's like pushing in a spring. If you release the spring, you get the energy back. If they were connected with a little string.
Okay, do you understand that? What he's saying is, with this charge, you have a positive charge here with a 1 on it, and a positive charge here with a 2 on it. These two are pushing each other away. They don't want to be near each other because they're both positive. And he's explaining that right now.
String would be stretched. Take scissors, cut the string, they fly apart again. So I have put work in there. That's what we call electrostatic potential energy. So let's work this out in some detail, how much work I have to do. Well, we first put Q1 here. If space is empty, this doesn't take any work to place Q1 here. But now I come from very far away. We always think of it as infinitely far away. Of course, that's a little bit of exaggeration. And we bring this charge Q2 from infinity to that point P. And I, Walter Lewin, have to do work. I have to push and push and push. And the closer I get, the harder I have to push. Finally, I reach that point P. Suppose I am here, and this separation is little r. I've reached that point. Then the force on me, the electric force, is outwards. And so I have to overcome that force. And so my force, F Walter Lewin, is in this direction. And so you can see I do positive work. Force and the direction in which I'm moving are in the same direction. I do positive work. Now, the work that I do can be calculated. The work that Walter Lewin is doing in going all the way from infinity to that location P is the integral going from infinity to radius r.
Okay, and this is where he's going to get into the math googly garb. I'm going to play it. So just in case there's any tidbit and gold nuggets, I'll stop it and see if I can. Every time I watch him, though, I hear something new. But yeah, just try and stay there. I know it's hard to keep your attention when they start talking the math, googly garb.
R to infinity, is it the same? One and the same thing. Let's calculate this integral, because that's a little easy. We know what the electric force is. Coulomb's law. It's repelling. So the force and the r are now in the same direction. So the angle theta between them is 0. So the cosine of theta is 1. So we can forget about all the vectors. And so we would get then that this equals Q1, Q2, divided by 4 pi epsilon 0.
Epsilon 0.
And now I have downstairs here an r squared. And so I have the integral now, dr.
Yeah, it's just math. This is all the stuff that I...
Capital R to infinity.
At least I don't care
and this
to
integral
know. This is all the theoretical...
R, which I have to evaluate.
This is math explaining
R and infinity.
What
and when I do that, that becomes plus 1 over capital R. Right? The integral of dr over r squared, I'm sure you can all do that, is minus 1 over r. I evaluate it between r and infinity, and so you get plus 1 over r. And so you...
And I'm not saying there isn't knowledge within there alone. Understanding what he's saying, and if you understand what he's saying, that's great. It's like, for me, it's like playing guitar. I don't want to be a master soloist, you know. I just want to be able to play rhythm guitar and sing and have a good time and, you know, enjoy myself. So that's how I do it. And with this, I just want to understand it, how it works in nature, more or less. I don't need to be able to explain it mathematically. That's why I just kind of... I'll be talking over him when he's doing this kind of stuff, trying to listen for those golden nuggets is what I'm saying.
Which is the energy, that the work that I have to do to bring this charge at that position. That U is now Q1 times Q2 divided by 4 pi epsilon 0 divided by that capital R. And this, of course, is a scalar, it is work, number of joules. If Q1 and Q2 are both positive or both negative, I do positive work. You can see that. Minus times minus is plus. Because then they repel each other. If one is positive and the other is negative, then I do negative work. You see that comes out, this is sign sensitive. Minus times plus is minus. So I can do negative work if the two don't have the same polarity. I want you to convince yourself that if I didn't come along a straight line from all the way from infinity, but I came in a very crooked way, finally ended up at point P, that point, that the amount of work that I have to do is exactly the same. You've seen a parallel with 801 where we dealt with gravity. Gravity is a conservative force. And when you deal with conservative forces, the work that has to be done in going from one point to the other is independent of the path. That is the definition of conservative force. The electrostatic forces are also conservative, and so it doesn't make...
Okay, did you hear that? What he was talking about gravity, and then right afterwards he says, he explains that they are independent forces, gravity. Then he says the electrostatic forces are independent forces as well. Again, electricity acting very much parallel to what they call gravity.
Any difference whether I come along a straight line to this point or whether I do that in an extremely crooked way and finally end up here. That's the same amount of work. Now, if we do have a collection of charges, so we have pluses and minus charges, some pluses, some minus, some pluses, minus, pluses, pluses, then you now can calculate the amount of work that I, Walter Lewin, have to do in assembling that. You bring one from infinity to here, another one, and you add up all that work. Some work may be positive, some work may be negative. Finally, you arrive at the total amount of work that you have to do to assemble these charges. And that is the meaning of capital Q. Now I turn to electric potential.
Okay, you got to remember that now. He was talking about electrostatic potential. So that just means the amount of work it takes to get from one point to another. The electrostatic potential. It doesn't matter how many swirls or this or that it takes you to get there. Like he said, you see how he drew on the board. I got from this point to that point. Even if I go a straight path or I go in a big giant squiggly line, the electrostatic potential is the same. It was the force it took to get this charge from here to that charge, close enough to that charge. That is electrostatic potential. He'll show us some demonstrations here in a little bit. It'll kind of, we just got to make sure we know the difference between electrostatic potential energy and then electric potential. Very, very different.
And for that, I start off here with a charge which I now call plus capital Q. Located here. And at a position P, at a distance R away, I place test charge, plus Q. Make it positive for now, you can change it later to something negative. And so the electrostatic potential energy, we know already, we just calculated it, that would be Q times Q divided by 4 pi epsilon 0 R. That's exactly the same that we have. So the electric potential, electrostatic potential energy is the work that I have to do to bring this charge here. Now I'm going to introduce electric potential. Electric potential. And that is the work per unit charge that I have to do to go from infinity to that position. So Q doesn't enter into it anymore. It is the work per unit charge to go from infinity to that location P. And so if it is the work per unit charge, then this little Q disappears. And so now we write down that V at that location P. Potential, electric potential at that location P, now only Q divided by 4 pi epsilon 0 R. The known Q has disappeared.
All this math.
It is also a scalar.
No.
This has unit joules. The unit here is joules per coulomb. I have divided out one charge.
Joules per
It's work per
coulomb
unit
or
charge.
volts, named after Voltaire.
No one would ever call this joules per coulomb. We call this volts, called after the great Volta. Did a lot of research on this. So we call this volts.
Work per unit charge. Volts.
But it's the same as joules per coulomb. If we have a very simple situation like we have here, that we only have one charge, then this is the potential anywhere, any distance you want from this charge. If R goes up, you're further away, the potential will become lower. If this Q is positive, the potential is everywhere in space positive for a single charge. If this Q is negative, everywhere in space, the potential is negative. Electrostatic potential can be negative. The work that I do per unit charge coming from infinity be negative.
I'm going to jump back for just a little bit.
The potential charge.
I think I heard something in there.
Then this is the potential anywhere, any distance you want from this charge. If R
work per unit charge at any distance
goes up,
I don't know.
Further away, potential will become lower. If this Q is
okay.
positive,
so it's the distance, R, okay? If that changes, since it's on the bottom, if the distance gets larger, the work per unit charge will get less. The voltage will be less. And the closer you get, the stronger the charge. Okay.
the potential is everywhere in space positive for a single charge. If this Q is negative, everywhere in space, the potential is negative. Electrostatic potential can be negative. The work that
electrostatic potential can be negative. Now, I've never heard him say that before, and I've watched this 5 times, and I never crossed my mind. I never picked it up. I was probably thinking about something else, about the volts. The electrostatic potential can be negative. So our negative ground can be causing electrostatic potential.
Do per unit charge coming from infinity would be negative, if that's a negative charge. And the potential, when I'm infinitely far away, this R becomes large, is 0. That's the way we define ours.
Okay, so once, pretty much infinitely would be once you got to 0 and beyond. I mean, mathematically, I don't like the whole infinitely.
0.
It's a mathematical term.
So you can have positive potentials near positive charge, negative potentials near negative charge, and if you're very, very far away, then potential is 0. Let's now turn to our Venn graph. The hollow sphere has a radius R of 30
so
centimeters.
Cool. That's amazing.
And I'm going to put on here plus 10 microcoulomb. It will distribute itself uniformly. We will discuss that next time in detail, because it's a conductor. We already discussed last lecture that the electric field inside the sphere is 0, and that the electric field outside is not 0, but that we can think of all the charge being at this point here. Plus 10 microcoulomb is all here, as long as we want to know what the electric field outside is.
Okay, now, did you hear that? He talks about this before. The electric field on the inside of a hollow sphere is always 0. None of the charge will gather on the inside of that sphere, hollow sphere. Now, if it is a perfect sphere, all of the electricity will, and it is a conductor, it will gather uniformly around the outside edge, equally. And he didn't say it, but it always radiates straight out at 90 degrees from the surface. Always perfectly straight out it starts.
So you can forget the fact that it is a sphere. And so now I want to know what the electric potential is at any point in space. I want to know what it is here, and I want to know what it is here at point P, which is now a distance r from the center. And I want to know what it is here, distance little r from the center. So let's first do the potential here. The potential at point P is an integral going from r to infinity. If I take the electric force divided by my test charge Q dot the r. But this is the electric field.
This is the stuff that just gets so...
Force times distance is work, but it is work per unit charge. So I take my test charge out. So this is the integral in r to infinity E dot dl, the r. Sorry.
But this is his job, you know.
And that's a very easy integral because we know what E is.
Was his job, I should
Electric
say.
field is done several times, follows immediately from Coulomb's law. And so when you calculate this integral, you get Q divided by 4 pi
Epsilon 0.
epsilon 0 r. Which is no surprise because we already had that for a point charge. So this is the situation if r, little r, is larger than capital R. Precisely what we had before.
Oh, this stuff gets so boring when he's doing this stuff. I know, I'm sorry, folks. You can't make it this part fun.
0.3 meters.
But there are little gold nuggets.
Microcoulomb, here the 30 centimeters, then you'll find 300,000 volts. So you get 3 times 10 to the 5th volts. If you take R equals 60 centimeters, double it, double the distance, potential goes down by a factor of 2, it's 1 over R, so it would be 150 kilovolts. And if you go to 3 meters, then it is 10 times smaller, then it is 30 kilovolts. And if you go to infinity, which for all practical purposes would be lobby 7, you go to lobby 7, then the potential for all practical purposes is about 0.
Okay, so here, hey Trav, how we doing, man? Low volume. Here, let me, oh, maybe I can turn, yeah, I can turn up a little bit more. Sorry about that. Hey, got a fish. So pretty much same thing. He's explaining the further away you get your electrostatic, or no, your electric potential goes down. He'll sum it all up right here. I know this is so boring watching this stuff, folks. It's hard, and I'll do 1 through 5, and then I'll go through and I'll pull out all the bits and I'll try to make them into a video or something. I'll see what I can do, or I'll at least like timestamp them, and we'll go through them and see all the really good juicy parts where he explains the stuff. But here we go. I think he's going to explain this pretty well right here, what he's saying.
Because R is so large that there's no potential left. So if I want to Lewin march from infinity to this surface of the Van de Graaff, and I put a charge Q in my pocket, and I march to the Van de Graaff, by the time I reach that point, I have done work. I multiply the charge now back to the potential. That gives it work again, because potential was work per unit charge. So the work that I have done then is the charge that I have in my pocket times the potential, in this case, the potential of the Van de Graaff. If I go all the way to this surface, which is 300,000 volts. If I were a strong man and I would put 1 Coulomb in my pocket, that's a lot of charge, then I would have done 300,000 joules of work by just carrying the 1 Coulomb from lobby 7 to the Van de Graaff. That's about the same work I have to do to climb up the Empire State Building. Famous mgh, my mass times g times the height that I climb. So I know how the electric potential
Yeah, I
goes
hear
with
you,
distance
Trav.
to one
It's
over our
just
relationship. Now I have arrived
blah,
at
blah,
the
blah, blah, blah.
Van de Graaff. I am at the surface with my test charge, and now I go inside.
No, it's definitely something you need
And
to
I
watch.
slosh around inside. I feel no force anymore. There's no electric field inside. So as I move around inside,
So inside
I
of a
experience
sphere,
no force.
a hollow sphere,
That means I do no work. So that means that the potential must remain
is no
constant.
electric field.
So the absence of an electric field here implies that the electric potential everywhere is exactly the same.
Okay, inside of a hollow sphere, the electric potential is the same everywhere. That's the juicy part we're going to pull out of that one. And he'll go on to say, let's see, what else?
Side is the same as on the sphere. No further work is needed in marching around with a test charge.
So once you get it there, it doesn't matter where inside you need to place it. It's just until you get to the edge, because inside there is no electric field. Okay.
And so for this special case, I could make a graph of the electric potential versus R. And this is then the radius of the Van de Graaff. And that will be a constant all the way up to this point. And then it would fall off 1 over R here. And for the numbers that we have chosen, the potential at the maximum here would be 300,000 volts. Just as when you look at maps, where you see contours of equal height of mountains, which we call equal altitudes, here we have surfaces of equipotential. And if you had a point charge, or if you had the Van de Graaff, these surfaces would be concentric spheres. The further out you go, if the charge is positive, the lower the potential would be.
Okay, hold on. What did he say just now? I gotta jump back. I'm sorry.
Where you see
He's talking about the maps
contours of equal
with different
height
mountains.
of mountains, which we call equal altitudes. Here we have surfaces of equipotential.
Okay, so what he's saying, equipotential energy. I don't understand what he's talking about here. I'm sorry.
And if you had a point charge, or if you had the Van de Graaff, these surfaces would be concentric spheres. The further out you go, if the charge is positive, the lower the potential would be. It would be nicely spherical surfaces. Suppose now we had...
Oh, okay. So he's saying if it were like a contoured map of mountains and you did have it a perfectly spherical Van de Graaff, then the electric field would follow those contour lines and be perfect concentric circles as well, as it got weaker and weaker and weaker. Okay, now I understand what he's saying. So, yeah. Did you get that? Okay, we'll go back and listen to it one more time. And after you heard what I said, maybe it'll help a little bit. I don't know. I hope. He's going to talk about having like mountains of different sizes.
Just
The
as when you look
energy
at maps,
will gather on
where you
surfaces
see
like that as well.
contours of equal height of mountains, which we call equal altitudes, here we have surfaces of equipotential. And if you had a point charge, or if you had the Van de Graaff, these surfaces would be concentric spheres. The further out you go, if the charge is positive, the lower the potential would be. It would be nicely spherical surfaces.
Okay. So the further away, if it's positive, the further away you get from the surface of the Van de Graaff, it would fall off. And it does it since it's a nice sphere shaped. All of the energy is, and it is a conductor, all of that energy will go off in nice spheres. And it'll gradually get lower and lower. The equipotential energy will get lower and lower the further you get away until you get to zero. But it will all go off evenly in all directions in nice spheres. Just like the perfect shape of the Van de Graaff is what he's saying. Now he's going to go say if you have, watch, this is why he's explaining that.
Suppose now we had more than one charge. We had a plus Q1 charge, Q2 charge, for instance. And you're being asked now, what is the potential at point P? Well, now the electric potential at point P, Vp, is the potential that you would have measured if Q1 been there alone. You have to add the potential that you would have seen if Q2 had been there alone. Just adding work per unit charge for one is work per unit charge of the other. And if this is negative,
oh, no worries,
then
Battlefish.
This quantity is negative.
Yeah, they'll be here to watch, man. No worries.
So when you have configurations of positive
I appreciate
and
you
negative
stopping
charges,
by. You have a good
then
one.
Of course, depending upon where you are in space, if you're close to the plus charge, potential is almost certainly positive. The 1 over r is huge. If you're very close to the negative charge, then the 1 over r, this little charge will dominate, and so you get a negative potential. So you have surfaces of positive potential, and you have equipotential surfaces of negative potentials, and so there are surfaces which have zero potential. They're not always very easy to envision. But what I want to show you is some work that...
Okay, now there was something in there I think that he said that's worth having him repeat there. 1949, we'll go back to like 1930 maybe. Mind you.
And the 1 over r, this little charge will dominate, and so you get a negative potential. So you have surfaces of positive potential, and you have equipotential surfaces of negative potentials, and so there are surfaces which have zero potential. They're not always very easy.
So you have surfaces with positive, surfaces with negative, and surfaces with zero charge, which are not easy to envision, he says.
To envision. But what I want to show you is some work that Maxwell himself did in figuring out these equipotentials. So I have here a transparency of publication by Maxwell You see a charge, let's assume it is +4 and +1, could be -4 and -1, but let's assume they're plus. And you see the green lines, which we've seen before, which...
Now look, he's going to explain some really neat stuff, but I just want to show you before. Think of these as, I don't know, almost like human beings, if you would, standing in a room. Some give off more energy than others. Some is positive, some is negative. If you get enough positive in a room, the amount of energy, some rooms you walk into and it can suck the life out of you. It's so dead and boring. In other ones you walk in and it's all alive and bright and vibrant. And think of it kind of like that. These are just electricity is everywhere, controlling everything. So you can apply this stuff to just about everything. Remember that. So we're just learning how electricity, a charge of electricity will act near another charge of electricity, whether it be the same or the opposite. We're just learning the very, very basic understandings of how all this stuff works. But in this drawing alone, you can see the number of lines kind of tell you how strong it is in these pictures. If it didn't have a 4 up there and a 1, and they didn't make it bigger, and it was just a point, and then you had lines coming out of it, he'll explain all of this. But you can apply this stuff to so many different thoughts and so many different ways of how things work and how, I don't know. I'm sorry, I'm rambling.
Try the field lines. Don't pay any attention to the green field lines now. The red lines are equipotentials, and you have to rotate them about the vertical because they are for surfaces.
Okay, the red lines are the equipotential.
This is three-dimensional. I have not drawn all the equipotential surfaces in red because they become too cluttered here. I've tried to put most of them in red. Since this charge is positive and that charge is positive, everywhere in space, no matter where you are, the potential has to be positive. There's not a single point where it could be negative. If you are very far away from the +4 and the +1, then you expect that the equipotential surfaces are spheres because it's almost as if you were looking at a +5 charge. So it doesn't surprise you that when you go far out, that you ultimately get spherical shapes. When you're very close to the plus.
Now think about that. And think about things like the sun and things like that. It could be multiple things, but once you get so far away from it, it all looks like one. Lots of things are like that.
+4, they are perfect spheres. When you're very close to the +1, they are perfect spheres. But then when you're sort of in between, neither close to the +4 nor to the +1, they have this very funny shape. It reminds me the shape of this balloon a little bit. Sort of like this. Surface, which is most unusual, equipotential surface, which here has a point where the electric field is 0. Sort of like.
So there's a point in between these two positive charges where the electric potential, not the electrostatic, but just the electric potential is 0.
Twisting the neck of a goose, you get something like this. And so you have here a surface which has a point here, and it is exactly at that point where the electric field is 0. That does not mean that the potential is 0. Of course not. Potential is positive here. If you come...
Oh, the electro... Okay, hold on. Let me see what he said there. I got that wrong. Oh, I don't know how far back I went.
But then when you're sort of in between, neither close to the +4 nor to the +1, they have this very funny shape. It reminds me the shape of this balloon a little bit, sort of like this. Okay. And there is one surface which is most unusual, equipotential surface, which here has a point where the electric field is 0. Sort of.
Okay, so the electric field is 0. The equipotential will still be positive. But the electric field in between these two different charges is 0. Totally different things, the electric field.
Sort of like twisting the neck of a goose. You get something like this. So you have here a surface which has a point here, and it is exactly at that point where the electric field is 0. That does not mean that the potential is 0. Of course not. Potential is positive here. If you come with a positive charge from the lobby 7 and you have to march up to that point, you have to do positive work. You have to overcome both the repelling force from the +4 and the repelling force from the +1. But finally, when you reach that point, you can rest because there's no force on you at that point. That's what it means that the electric field is 0. It does not mean that you haven't done any work. So never confuse electric fields with potentials. I want to draw your attention to the fact that the green lines, the field lines, are everywhere perpendicular to the equipotentials. I will get back to that during my next lecture. That is not an act.
Okay. The electric field lines are always equipotential. Did you hear what he said there? So important. So important. When it comes, oh, this is gold. This is one of those gold nuggets that you got to get into your head.
From the +1. But finally, when you reach that point, you can rest.
The green lines are the electric field lines.
That's what it means.
The red are the
It does not mean that you haven't done any
electric potential.
Never confuse electric fields with potentials. I want to draw your attention to the fact that the green lines, the field.
So think of the electric field lines as like, oh, what would you consider them? Like pieces of string I don't even know what would do it. Okay, if you think of like a mirror ball with all these bright lights shining straight out of it, okay? If there was no other electric charges around or any other field lines to mess with it, those would go on infinitely. Those would be your electric field lines. They would shoot straight out from the object. Now your electric potential would be, since it'd be a perfect sphere, would be like circles going out around it equally. You know what I'm saying? Circles getting bigger and bigger and bigger, and the electric potential getting smaller and smaller and smaller the further away you get, kind of like a light bulb. It doesn't matter what side of the light bulb you're on, if it's perfectly clear, you know, whatever, but you're going to get the same amount of light. And the further away you get, the weaker that light source will get. That's your electric potential. And then your electric field lines are actually, they're different. And they interact with each other. You saw that, but when you bring more charges together, the electric potential changes, but the electric field lines are, and listen to what he says here. He says the electric field lines are always equipotential, or pretty much he's saying they lie 90 degrees parallel to the electric potential lines. The electric field lines and the electric potential lines always crisscross at 90 degrees. So the electric field will always hit its surface of its object at 90 degrees and will always emanate off of that depending on the field. Oh, it's so beautiful, electricity, and the way it all works.
Field lines are everywhere perpendicular to the equipotentials. I will get back to that during my next lecture. That is not an accident. That is always the case. Now,
Hi, Ruby.
Maxwell shows you
Welcome.
something that is a little bit more complicated. Here, he calculated for us the equipotential surfaces. The red ones are the surfaces. Again, you have to rotate them about the vertical, make it three-dimensional. Now we have a -1 charge and a +4. And so whenever it is red, the surface, the potential is positive. And whenever I have drawn it blue, the potential is negative.
Remember, negative sucks like a vacuum, while positive blows like a hairdryer.
First, if we were very far away from both the +4 and the -1, you expect to be looking at a charge +3. And so if you go very far away, for sure, the potential is everywhere positive, and you expect them to be spherical. You look here, very far away from the +4 and the -1, indeed this has already the shape of a sphere.
So all electric charges eventually become spheres, is what he's saying. Once you get far enough away from all the electricity that's being created, it would look like a sphere. Huh. So around your body, there's a sphere. That is, that bumps into others and this and that, and it always, gosh, I wish I could see the electric field lines. That would be amazing.
So that's clear, that the +4 and the -1 far away behave like a +3. If you're very close to the +4, you get nice spheres around the +4, positive potential. If you're very close to the -1, notice that the blue surfaces are almost nice spheres, but now they're all negative, very close to the -1, so a negative potential. There is here one surface which now has 0 potential. If you're negative potential close to the -1 and you have positive potential very far out, you got to go through a surface where it's 0. And so there is here a surface, I still have put it in blue, which is actually everywhere on this surface, the potential is 0. Is the electric field 0 there? Absolutely not. Electric field should not be confused with potential. What it means is, but now they're all negative, very close to the -1, so a negative potential. There is here one surface which now has 0 potential. Has to be, because if you're negative potential close to the -1 and you have positive potential very far out, you got to go through a surface where.
So, and it looks like it's very close to the -1, and it's like circling it. There is 0 potential. Doesn't mean there is no field line, electric field there, or the green lines going through it. It just means that you could put something there and you wouldn't have to have energy on it. What does that mean? Electric potential. I know there's still something I'm not grasping in here, folks. Still learning to.
0. And so there is here a surface, I still have put it in blue, which is actually everywhere on this surface, the potential is 0. Is the electric field 0 there? Absolutely not. Electric field should not be confused with potential. What it means is that if you take a test charge in your pocket and you come from infinity.
Wow. So just think. I'm sorry, I got to share this with you. I just had like a little epiphany. If we have a strong enough electric field, a strong enough charge above us, and then a strong enough charge below us, like say a very strong positive charge above us, say something that might be creating the sun or something, I don't know, maybe it's a plate, I don't know, and beneath us a negative like the ground, there'd be a strong flow going down, and our electric fields that we are putting off on ourselves cannot just go floating up. Like we can't just fly whenever we want to. Things can't just do that because of this electric field pushing down our electric field. You know, it's always going to be pushing down upon us because it's that much greater and stronger. Yes, right here near each other, the fields interact, but there is always this constant pushing, this flow from a positive to a negative. And if it's that great, you just couldn't break it, really. Wow.
And you walk to that surface, that by the time you have reached that surface, you've done zero work. That's what it means. Potential is zero. There is here one point, which we discussed earlier in my lectures, where the electric field is zero. The potential is not zero there. Potential is definitely positive here, because here was the zero surface. Here is already positive surface, and this is a positive surface, so the potential is positive. However, if you reach that point, there's no force on your charge. So that means electric field zero. It is not so easy, of course, to calculate these surfaces. Maxwell was capable of doing that 110 years ago, and nowadays we can do that very easily with computers.
Yeah, theoretical mathematics.
Equipotential surfaces, which have different values, can never intersect. Plus 5-volt surface can never intersect with a +3 or a -1. You think about why that is. Why that is. It would be a total violation, conservation of energy. So equipotential surfaces, different values can never.
Oh.
However, if you reach that point, there's no force on your charge. So that means electric field zero. It is not so easy, of course, to calculate these surfaces. Maxwell was capable of doing that 110 years ago, and nowadays we can do that very easily.
So if you could find a place where your electric field is zero, then you can float. In lecture 3, he went, oh wow, so yeah, if we went down far enough, I don't know. There's so much to contemplate on what we've learned already, just in the first 3, and now just the 4th one.
With computers.
This is what I wanted to hear right here.
Equipotential surfaces, which have different values, can never intersect.
Okay, equipotential surfaces that have different values can never intersect. So if you have a positive sphere over here and a negative sphere over here, they'll discharge before they can connect. I'm willing to bet.
+5.
Yeah, they would. They could never cross. Wow, so a positive charge can never cross into a negative charge.
5-volt surface can never intersect with a +3 or a -1. You think about why that is. Why that is. It would be a total violation, conservation of energy. So equipotential surfaces, different values can never.
Well, no, because they don't cross lines because the one cancels the other one out. Conservation of energy. Positive is absorbed by a negative. You know, they never just cross paths and don't interact. It doesn't work that way. It's a law.
Interesting. All right. So you've seen that for the various charge configurations, the equipotential surfaces have very complicated shapes and cannot always be calculated in a very easy way. Now comes the question, why do we introduce electric potentials? Who needs them? And who needs equipotential surfaces? Isn't it true that if we know the electric field vectors everywhere in space, that determines uniquely how charges will move, what acceleration they will obtain? That means how their kinetic energy will change. And the answer is yes.
Okay, did you hear that? If we know how the electric field moves, we'll know how electric charges will move. And their kinetic energy.
Yeah, you know the electric field everywhere in space, sure. Then you can predict everything that happens with a charge in that field. But there are examples where the electric fields are so incredibly complicated that it is easier to work with equipotentials. Because the change in kinetic energy, as I will discuss now, on the change in the potential when you go from one point to another. So you will see very shortly that sometimes if you're only interested in change of kinetic energy and not necessarily interested in the details of the trajectory, then the potentials come in very handy. Never confuse U, which is electrostatic potential energy, with V, which is electric potential. This has unit joules, and this has unit joules per coulomb, we call volts. If I have a collection of charges, pluses and minuses, U has only one value. It is the work that I have to do to put all these crazy charges exactly where they are. But the electric potential is different here, from there, to there, to there, to there. You're very close to a plus charge, you can be sure that the potential is positive. If you're very close to a negative charge, you can be sure that the potential is negative. But U has only one number, one value. They're both scalars.
So electrostatic potential has to do with Okay. So think of it as maybe a room. You have a square room. And I don't even know. I don't know how to explain it with the electrostatic. I don't understand the electrostatic potential nearly as well as the electric potential.
Don't confuse one with the other.
But they're very different. One is the overall power,
field,
and the other one is
matter, like a piece of chalk, wants to go from high potential to low potential. If I just release it with zero speed, there it goes. High potential to low potential. In analogy, positive charges will also go from a high electric potential to a low electric potential. And of course, this is unique for electricity. Negative charges will go from a low potential to a high electric potential.
that is unique to electricity. A negative potential will go towards a higher potential. We're at 2928. I wanted to hear something back here anyway.
In a gravitational field, matter, like a piece of chalk, wants to go from high potential to low potential. If I just release it with 0 speed, there it goes. High potential to low potential. In analogy, positive charges will also go from a high electric potential to a low electric potential. And of course, this is unique for electricity. Negative charges will go from a low potential to a high electric.
So kind of like helium, totally defying gravity. Another thing that kind of shows us that electricity controls a lot more things. Electricity is a lot more powerful here on Earth. Helium has a negative potential energy, just like the Earth is negative. So it's pushing itself away, trying to get to the positive. This is unique in electricity. Gravity doesn't do this, you know?
Electric potential. Suppose I had a position A in space, and I had another position B, and I specify the potentials. So here we have A, potential VA, and here we have point B, where the potential VB. By definition, the potential of VA, as we discussed before,
it goes into his math,
is the integral. By the way, if these are separated by some random distance r, whatever you want. So the potential of A is defined.
This is a lot of the theoretical mumbo jumbo. I'm sure you'll throw epsilon 0 in there. And
that is the definition of the potential of A. There's an E here, which is force per unit charge. So it is not work. If they were forced the R, it would be work, but it is force per unit charge that makes it E. So the potential of B, for definition, the integral from B to infinity of E dot dr. And so therefore, the potential difference between point A and B,
this
VA
stuff drives me nuts.
minus VB equals the integral from A to B of E dot dr. And for reasons that I still don't understand after having been in this business for a long time, books will always tell you they reverse VA and B, so they give you VB minus VA. And then they say, well, we have to put a minus sign in front of the integral, the same thing. So books always give it to you in this form. But it is exactly the same. You realize that. This is the two equations that I have here.
Anything he circles in pink
Are the same. VA minus VB is the integral from A to B of E dot dr. If I flip this over,
always important when he does
all
that.
I have to do is put a minus sign here, and the two are identical. Notice that if there is no electric field between A and B, they have the same potential, of course. But when you march from A to B with a charge in your pocket, no work is done, so the potential remains the same.
And there is no place where there is no electric field, so this is all
I will change this
theoretical.
dr to a different symbol, which
You
I call
know,
dl.
this is the math stuff that I just...
dr would mean that we go from A to infinity along this straight line, And then we go from B to infinity along the straight line. But it makes no difference how you go. If you go from A to B, this potential difference, and you go in this way, then VA minus VB is not going to change. And so if now I introduce here a element dl, is a small vector, and if the local E vector here is like so, at this point here, then VA minus VB is then the integral of E dot dl. In other words, I can replace the R by an L, and you may choose any path that you prefer. That's the way that we will show you this equation most of the time. So it makes no difference how you march, because we are dealing here with conservative fields. So let's now make the assumption that VA is 150 volts, and that VB, for instance, is 50 volts. So it's a very specific example.
Okay, specific examples. I like these.
What does it mean now? It means that if I put plus Q charge in my pocket, and I come all the way from lobby 7, and I walk up to point B, so Walter Lewin, plus Q charge in his pocket, goes from lobby 7 to point B. I have to do work, and the work I have to do is the product of my charge Q with the potential. So that is Q, the work I have to do is Q times VB. So in this case, it's 50 times Q, whatever that charge is that I have in my pocket. This is in joules. Now, I go from lobby 7.
Not volts, this is
point A.
for you.
I have to do more work. I have to do 150 Q joules of work. You can think of it, I first come to B, I'm already exhausted. I have to put in another work to get all the way to point A. So you can imagine if I have this plus Q charge at point A, where it is at a higher potential, it wants to go back all by itself to B. It wants to go from a higher potential to a lower potential. Look, the E vector is in this direction. Positive.
Okay, so even if they're all positives, it's going to want to go to the less positive area. So not so that's kind of like your layers of atmosphere there. They all will level out equally. You know what I'm saying? If you have 3 positive charges, and you have one, like he said, that's 150 and one that is 50, and you take a positive charge, whether it could be 1, and you go past the 50 and start going towards the 150, it will go you let that charge go, it will go back towards the 50 just to get away from that 150 up to a certain point, I'm assuming. Let's see what he says.
Charge will go to a lower potential. And as it moves from A to B, energy is released. How much energy? Well,
energy is released. Did you hear that? So once we go from A, we take the charge and we let it go because, okay, energy is released. Oh, let's see.
This is the amount of work I have done to get to A. This is the amount of work I did to get to B. And so if now the charge goes back from A to B, it's the difference that
you have positive 100
in terms of kinetic energy. It's a change in potential energy.
Or a negative.
And that change in potential energy, so the change in potential energy, when the plus Q charge goes from A to B, that change is Q times VA minus VB. QVB at point B and QVA.
So 100, yeah.
At point A. So this is the potential energy that is in principle available if the charge moves from A to B. And you remember from 801, the work energy theorem, we deal with conservative forces, then the sum of potential energy and kinetic energy of an object is the same. That's also true for gravitational force.
Isn't it so neat how similar gravitational and electric forces are? Let's see, 3706. There's a jewel in here that I heard, I know. So we're going to jump back just a little bit and listen to this, what he just said. Make sure you got your ears open now.
Is in principle available if the charge moves from A to B. And you remember from 801, the work energy theorem, we deal with conservative forces, then the sum of potential energy and kinetic energy of an object is the same. That's all.
When you're dealing with conservative forces, the sum of potential and okay, listen to this part. Sorry, I should have
is in
stopped
principle available if the charge moves from A to B. And you remember from 801, the work energy theorem, we deal with conservative forces.
Work energy
then the sum
theorem.
of potential energy, kinetic energy of an object is the same. That's also true for gravitational force.
Potential
In other words,
and kinetic
this
energy
difference
are
in
the same.
potential energy that becomes available, like potential energy becomes available when I drop my chalk from a high potential to a low potential.
Ah, so you can create, what he's saying is you can create energy going from a high potential area to a low potential area. This is kind of why the wind blows, is this right here, going from a high potential to a low potential. Things going from high pressure to low pressure. There's energy that is being released in there that you can gather. You can gather the wind, you know? There's things out there that we can gather. Wow. Heat source, you can gather, you know? Wow. That's cool.
That's converted to kinetic energy. So this difference now is also converted into kinetic energy of that moving charge. And so that would be the kinetic energy at point B minus the kinetic energy at point A, which is really the work energy theorem. It's the conservation of energy. Now, any piece of metal, no matter how crummy or dented it is an equipotential, as long as there is no charge moving inside the metal. And that's obvious that it's an equipotential, because these charges inside the metal, these electrons, when they experience an electric field, they begin to move immediately in the electric field, and they will move until there is no force on them anymore, and that means they have effectively made the electric field zero. So charges inside the conductor always move automatically in such a way that they kill the electric field inside. If the electric field hadn't been zero yet, they would still be moving. And so each metal that you have, no matter where you bring it, as long as there are no electric currents inside, will always be an equipotential. So I can take a trash can and bring it into an external field. And then very shortly after I've brought it in, when things have calmed down, the trash can will be an equipotential, and the electric field inside the metal will everywhere be zero.
Okay, so it doesn't have to be a perfect sphere. Like you said, a metal trash can. You can cancel out the electric field once everything settled down, and all that, it has to be metal, and all that charge would then uniformly gather along the outside and start vibrating out the inside would then have 0 electric field charge.
So I could, for instance, attach point A to a trash can, metal trash can. The whole trash can would be at 150 volts, and I could put point B, make it part of my soda, which is also made of metal. And so the whole soda would be at 50 volts, and the entire trash can would be at 150 volts. I place the whole thing in vacuum, and now I release an electron at point B. An electron. Electron wants to go to higher potential. Proton would go from A to B. Electron wants to go from B to A. And so now, energy.
Okay, now why? Because a proton is positive and an electron is negative. So if you have the electron that is negative, it's going to want to go to a higher potential source. Like if you have a cold source, but I don't think that happens with cold. I think heat goes to cold, not cold to heat. That's why he said this was unique to electricity. Is it just a high pressure system that moves into a low pressure system? When it comes to pressure, I'm not sure about that stuff. Okay, let's see what else he's got to say here.
Is available, the electric potential energy is available, and the electron will start to pick up speed and finally end up at A. Now, how it will travel, electric field configuration is enormously complicated between the can and this trash can. Amazingly complicated. If you were to see the field lines, it would be weird. But if all we want to know is what we...
No, it's not like Neo seeing the Matrix. It'd be even more. It's the electric field. Gosh, I wish I could see it. It would be like strings of spaghetti connecting everything almost, and showing the positive and negative energies all intermingling and combining, and wow, that would be cool.
The kinetic energy is what the speed is with which this electron reaches the can. So what? Then we can use the work energy theorem and find out immediately what that kinetic energy is. Because the available potential energy is the charge of the electron times the potential difference between these two objects. Well, the charge of the electron is 1.6 times 10 to the minus 19 Coulomb. The potential difference is 100 volts. And that is the difference in kinetic energy. If I assume that I release the electron at 0 speed, then I have immediately the kinetic energy that it has at point A, which is 1/2 m of the electron times the speed at A squared. So now you see that, accepting the fact that we know the equipotentials, we can very quickly calculate the kinetic energy and therefore the speed of the electron as they arrive at A without any knowledge of the complicated electric field. If you put in the numbers for the mass of the
theoretically,
electron,
of course,
then, which is 9 times 10 to the minus 31 kilograms, then you find that this speed is about 2% of the speed of light, potential speed.
Amazing teacher, though. Just amazing. I love Walter Lewin.
All our potentials, electric potentials, are defined relative to infinity. That means at infinity, they are 0. That is because of the 1/r relation. That's very nice and dandy, and it works. However, there are situations whereby it really doesn't matter where you think of your 0. Remember with gravity, we had a similar situation. With gravity, we always worried about difference in potential energy, but sometimes we call this 0, and this plus. Sometimes you call this plus and this minus. It doesn't really matter because the change in kinetic energy is dictated only by the difference in potential. So it is very nice and dandy to call that 150 and to call that 50, but you wouldn't have find any different answer for the electron if you call this potential 100 volts and you call this one 0, or you call this one 0 and this one minus 100, or you call this one 50, this one minus 50. So the behavior of the electrons, of the charges, would of course not change. And because electrical engineers would always, per definition, hold the potential of the Earth 0 when they built their circuits.
So the electric potential of the Earth is 0, according to electric engineers.
Now I would like to demonstrate to you with the Van de Graaff.
Okay, here we go. Cool. We'll get into some demonstrations.
Get a strong electric field from
Only
the
a few minutes
radially
left,
outward
folks.
from the Van de Graaff. That you get a huge potential difference between this point here and this point there. If I have my numbers still there, hope I do, there they are. At the surface of the Van de Graaff, which takes about 10 microcoulomb, will be 300,000 volts right here. Here it would be 150,000 volts, and here, 3 meters from the center, about 30 kilovolts. So that means that if I place this fluorescent tube into that electric field, that there would be a gigantic potential difference between here and there, provided I hold it radially. If I hold it like this, then the potential difference between here and there
would be equal.
0, of course.
Yeah.
If I hold it tangentially, they would be both at the same
Distance.
electric potential.
Yeah.
But when I hold them radially, you will see, perhaps, that this fluorescent tube will show a little bit of light. Once you see light, it means that
But there's electricity flowing through it.
that gas. It means charge is moving. We haven't discussed current yet, but that's what it means. The current is flowing. And this current has to be delivered by the Van de Graaff. The Van de Graaff is only capable of providing very modest currents. So you're not going to see a lot of light. But I want to show you that you will see some light, no wires attached, just here.
And I've done this also with my Van de Graaff generator.
Tangentially, and you will see no light at all. So if we can make it a little darker as a start, and I'll start the Van de Graaff, then if Marcos comes to make it completely dark when necessary, because the light is so little that we really have to make it.
Yeah, it'll light up that
dark.
fluorescent tube pretty nice.
I will put on a glove.
300,000 volts.
Reasons,
Mine was only.
So I don't think it will do me much good.
250,000 volts.
Notice I have here a piece of glass to be well insulated from the glass, so that I don't mess up the demonstration by. If I hold my fingers here, it will be very different than holding my hands here. So let's go first close with the light still on, and then. Okay, why don't you turn the lights off now, all the way off. Okay, I think you can see a glow. It's radially
see how it's gathering
now.
More where it's touching in the center.
And Marcos, can you give a little light? Okay, I will now go tangential. Can you turn the lights off? Now you see nothing, very little. Now I go radial again.
There it is.
There you go. Now, if I'm crazy, if I were crazy, then I would touch the end of this tube with my finger.
And it'll light up even more because he's
thereby
grounded.
allowing this current to go straight through my body to the earth, which may increase the light.
Yes, it will.
Let me try that. So
it doesn't hurt.
So I'm going to touch this fluorescent tube on your right side.
That it would only be 100,000 volts there. That's he's just playing. That's why it makes him a great teacher, though. Such a fantastic, fabulous teacher, folks.
make it easier for the current to flow, and you see very clearly.
And this happens also.
It lights up.
My playlist, Fun with Electricity, I show all this stuff.
Demonstration with a neon flash tube. And the neon flash tube I will place at the end of a fishing rod.
I'm going to spin it.
This neon flash tube we used during the first lecture when I was beating up students. But I've learned not to do that anymore.
Now listen to the crowd not find this funny what he just said. Where I beat up students, but I've learned not to do that anymore. This one kind of, I'll let you hear it again. Just, I don't know. I got a weird feeling when I heard it. Listen, see if you get that same feeling.
Fishing rod. This neon flash tube we used during the first lecture when I was beating up students. I've learned not to do that anymore. This takes several kilovolts to get a little bit of light out of it from one side to the other. Well, that's duck soup for the Van de Graaff. And so here I will actually start spinning it. And then when it is radially inwards, maybe you will see light. And when it is tangential.
So he's pretty much just showing you what he just showed. When I turn it sideways, the light goes out. When I
feel very good.
And I'll touch it and it'll shock me. And
I will do that again.
See, just a great teacher.
Okay,
you
so
know?
Marcos, if you make it dark, I'll give it a twist. Okay, radial, 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 radial. Okay. Now
Think about things in nature.
Ah! Okay, I touch it now. I touch it again. And I touch it again. And again. And
It's
again.
like holding it now.
You see, every time I touch it, lights me. And it gives a nice flash of light. So you see here, in front of your eyes, without any wires attached, that the potential difference created by the electric field, that those potential differences make these lights work. All right, see you.
Okay, so the electric potential difference, the volts, from, you know, not the electric field, but the electrical potential difference, the distance away from the electricity source going from higher to lower, and the potential energy between them, the flow of energy from one source to another, whether they both be positive, whether one be positive, one be negative, just the amount of difference in between them is enough to light up the gases inside of that tube there, is what he's saying. And when he puts it up next to the Van de Graaff, which is only one source, you know, there isn't a positive and a negative or a positive and a positive. It's just a positive there or just a negative there. It getting weaker and weaker the further away from that surface it gets. It's creating an electric potential from the closer point to the further away point. So that's your electric potential, just your distance from the source, from one point to another. So like he was saying, if it's 250 volts this far away from the Van de Graaff generator, and 150 volts at this far away from the Van de Graaff generator, then there will be 100 volts flowing in between these two areas right here, is what he's saying. That's your electric potential. Electrostatic potential, that's kind of the energy that it took to get the light into that position, sort of. I'm having trouble with the electrostatic potential. I'm gonna have to watch this one again. But that's it for the lecture. Like I said, Walter Lewin, an amazing teacher, folks. But I hope you learned a little bit about, now when he starts talking about voltage and electric potential, it just means from the source of energy, you know, say you plug your socket into the wall, well, no, from a yeah, the electric potential, electrostatic potential. Okay, it's static. There's no current. The electric static potential is just the energy it took to put a charge there. It's not. It's not like it's a current. It's okay. I'm gonna have to watch it again, and we'll go over all this stuff after we do one more. We'll do number 5, and then we'll go and have a brief run through of what we've learned so far. But I hope you enjoyed this one. I really did. Um, I just do them live, just in case for you diehards that like watching the stuff have any real questions or anything like that. Then I could do my best to answer them for you, or if you wanted me to go back or something like that. Um, but all these are here on YouTube. Walter Lewin, if you type that in, 802, it'll pop up his playlist with all these that we're watching here. This is his 4th lecture that we just got done watching. Um, if you're just starting here, I advise you to go back and watch the first 3. I go over them myself, or go ahead and watch them just on his channel. I kind of try to break it down and put stuff a little bit more into layman's terms. But yeah, just an amazing teacher. He's still teaching here on YouTube, so go subscribe to him. And he's still teaching. It's just amazing what some people are meant to teach, and he's one of those people. And I am I feel very blessed to be able to watch these lectures for free. I mean, here on YouTube, there's a lot more on YouTube than little videos with kittens, if you know where to look. But that's it, folks. I'm going to get out of here. I got to get up in the morning for Ironworks over on TFR. Love those guys. But yeah, this was a fun one. I've learned a lot. I'm going to listen to it again now. I still want to understand the electrostatic potential a little bit more, but electric potential, I get. I understand it a lot better than I did even before I started watching it this time. I had learned many things in here, but just defining the words, the terms, the definitions, getting them all down and getting them all straight. It's like learning another language. So we can learn them together. But thanks for joining me, everybody. Love y'all. And yeah, that's it. Good times for all here signing out. As always, thanks for watching.